You're here with another video with calculus. So here we go. We are talking this morning about volume of a solid, or the disk method. So what happens in these situations is you've got some function and it's rotating about an x-axis or a y-axis. So when you take that curve and you actually start to rotate it, then it becomes a solid figure. All right. So in that instance, we're taking a simple, and then as we rotate it, you can kind of picture if you took a flat surface and then rotated it around and around and around, you would get a solid figure. So that's what we're looking at. So let's look at some notation for these problems. Your volume is equal to the sum from I equals 1, your ith term. You're basically looking at how do we slice this function up as we go. And if we add an nth number of slices, if you will, and we keep going and going and going, and it could be 5 or 6 or 7 or an infinite amount of slices, as you've seen in like Riemann sums and some other things. You can do that with the sum of your change in x and your area of x sub I. So n is the number of cross sections that you'll have. The width is your change in x, how far apart is the width of these rectangles that we're moving along. And then a sub xi is the area of the base. And since we're rotating it around the x or y axis, then we have your area is equal to pi, because we can use pi or 3.14, but most of the time we'll just use the pi button, or leave it in terms of pi, times r squared, because that is the area of a circle. Now, how do we get the circle? Well, it's like if I take a curve and then I rotate it, I'll be dealing with all these. If I turn this and I'm looking at it one way and then I turn it, now all of a sudden I'm going to be looking at different circles, okay? So you can imagine that happening. So, or this is also equal to the integral, the antiderivative from a to b of your area dx. Okay, so let's look at an example here of what's happening. Example 1, it says find the volume of the solid formed by y equals square root of 2x and rotated about the x-axis from 0, the interval, over the interval of 0 to 4. All right, so here's our figure, right? Here's our function, if you will. And what we're doing is, in essence, we're going to rotate this. So we're going to take this and we're going to rotate it all the way around. So it'll look something like if I took this and I went down to negative root 6 and then I brought it back up, right? You would see that if I took an nth number of circles and I did this enough and enough and enough, we would form this solid here, right? So if I looked at it on the side as we go around and around and around, then we would get this side picture. But if I looked at it internally, what I would see is a circle formed by this outer curve. Okay, so that is where that, with that radius of the circle being the function y equals the square root of 2x. This becomes the radius, all right? So this is where our radius is from to create that circle. All right, so how do we put that together? Well, now that you have kind of a visual of what's happening, we're going to go from 0 to 4. We include pi because pi is in the equation, right? We have a circular area that we're looking for. Our r, which is our radius, is the function itself, the square root of 2x. We square that because the area of a circle is pi r squared, as we saw before, dx. And so once I square this, the root goes away. And so we have pi times 2x. Now I can bring the 2 pi out because they're just constants. So now I'm really integrating or finding the antiderivative of x, which becomes x squared over 2. And now I'm going to evaluate that from 0 to 4. So pi x squared 4. Once I plug in 4, I get 4 squared times pi, which is 16. And if I plug 0 in, or if I substitute 0 into this equation, I just get 0. So it's 16 pi minus 0, which is 16 pi. All right, let's look at another example and see what we can do here. All right, slide this over a little bit. See that. Now, here we have example number 2. Find the area, find the volume, I should say, of a solid by rotating the region bound by the given curves about the x-axis. So here's our function, y equals square root of 16 minus x squared, y equals 0, x equal 1, x equal 3, and so forth. So here's what we're doing. Here's the normal function. Now, if you recall, if I were to square both sides, this would be a circle, right, with a radius of 4. So that's how I knew how to draw this. I've got a radius of 4 in all of the directions, and I just drew the upper half because that's what this wants. It wants the positive root of this function. Now, the other boundaries are x equal 1 and x equal 3. And so I shaded in this red region right here, and imagine this wedge being rotated around and around and around. It's kind of like a doorstop maybe at your school. If you imagine that little piece right there being rotated around, you would form this solid that happens, and it's being rotated about the x-axis. So what we've got is the integral from 1 to 3 of pi. Our radius this time is the function, square root of 16 minus x squared. Well, once we square a root, the root comes out, and we get pi times 16 minus x squared. Now, I haven't even taken the antiderivative yet. All I've done is just square that function. So in there, now I can keep pi out, and now I'm going to integrate with respect to x, or find the antiderivative of 16. Well, that's just a constant, so it just becomes 16x minus, well, if I add 1 to that, remember the power rule there, which is I add 1 and divide by the same. So 2 plus 1 is 3 divided by 3. And I'm going to evaluate that from 3 to 1. So here it is. We substitute 3 in, we get pi times the quantity, all this, of 16 times 3, minus 3 cubed over 3, minus, remember, 3f of a minus f of b. So f of b will be 16 times 1 by substitution, and minus 1 cubed divided by 3. So 16 times 3 is 48. 3 cubed is 27 divided by 3 becomes 9, minus 16, and 1 cubed is just 1, so minus 1/3. And when you put that together and then multiply everything again by pi, we get 70/3 pi. All right, so that's a little bit how you can do the disk method, or find volumes of regions that have been rotated around a disk. Okay, so there's this picture again. Remember, you're just taking this and you're rotating it around, and the same thing goes for this picture here. All I would do is I would take this and rotate it around the x-axis, so it would create all these circles like this, okay? And it would just keep going and going. So I have a solid there. All right. Hope you've enjoyed that. Thanks again. Enjoy your day, and keep it mathy. Thanks again. Steve Dykstra, out.